Welcome to the deep dive. So, the world of computational pathology is really in the middle of this foundation model revolution. We have these incredible AI systems that can encode microscopic patterns, cell structures, tissue organization, into these powerful digital representations.
Right.
But there is this major clinical bottleneck, and it's a huge one. How do you scale that success?
It really is the difference between, say, reading a single paragraph and instantly reading an entire library. I mean, current models are fantastic at analyzing these tiny defined regions of interest, maybe 512 by 512 pixels.
Okay.
But the actual clinical data, these whole slide images or WSIs, they're gigapixel behemoths. Trying to analyze that massive scale with these old patchwork models is just, well, it's incredibly inefficient.
And it's not just the size, right? The constraints go beyond that. We have to talk about data scarcity.
Absolutely.
Because when you're dealing with common cancers, you might have hundreds of thousands of slides to train on. But for rare cancers, the ones affecting, fewer than 15 people per 100,000?
Right.
Your training set might be tiny.
Tiny. And traditional deep learning just falls apart when it can't generalize from that few examples.
Exactly. So that's the mission for this deep dive. We're trying to understand how one specific foundation model aims to solve both problems at once: scale and scarcity.
And that model is Titan, the transformer-based pathology image and text alignment network. This is a multimodal whole slide model, and it's designed to create a universal sort of general-purpose representation of any slide right out of the box.
Without all that painful task-specific fine-tuning.
Precisely.
Okay, so when we say foundation, we mean it's built on just a massive amount of data. Can you give us a sense of the scale of Titan's pre-training?
Oh, it's massive. So Titan was first trained on what they call the mass 340K dataset. That's 335,645 whole slide images.
Wow.
But here's the key innovation. They didn't just use images. They aligned the model with over 182,000 corresponding clinical pathology reports.
Okay, so image and text.
And on top of that, they added more than 420,000 synthetic captions, which were generated by another AI called PathChat. That specific blend of image, real text, and AI-generated text is really what gives Titan its power to generalize.
Okay, let's unpack that. It's a monumental undertaking. If the older models could only handle those tiny tiles, the little ROIs, how does Titan make that conceptual leap to understanding the entire gigapixel slide? What's happening in stage one?
So stage one is the vision-only pre-training phase. They call it Titan V. And the big conceptual shift here is moving away from training on raw pixels and moving towards training on feature summaries.
Okay, explain that for those of us who aren't machine learning engineers.
Of course. So think of the WSI, the whole slide, as being divided into hundreds of thousands of little non-overlapping patches.
Right.
Instead of feeding the raw pixels for each patch into the vision transformer, the VIT architecture, which would be way too slow, they use a powerful encoder to first summarize each patch. It turns it into a dense, 768-dimensional feature vector.
So instead of trying to read every single letter on a page, they're creating a really detailed summary sentence for every paragraph, and they're feeding the AI those summaries instead.
That is a perfect analogy. And these feature summaries, these vectors, they're then arranged into this huge 2D feature grid that perfectly replicates the tissue's physical layout on the slide.
So it preserves all that crucial spatial information that the patch-based models would just ignore.
Exactly. It keeps the context.
So that's the key then, context. How does it actually learn those spatial relationships in this massive grid?
The training approach is, it's really brilliant. It uses a method centered on knowledge distillation. You have a teacher model guiding a student model, transferring knowledge. But at the same time, the model masks out these random large areas of the feature grid.
It just hides them.
Yes, it hides, say, an 8,192 by 8,192 pixel region, and then forces the model to predict what's missing. By constantly predicting the structure and the features of those missing regions, Titan V learns an incredibly robust general-purpose representation of histology.
This is where that map analogy really clicks for me. If the WSI is a high-res map of a city, and the features are the detailed tiles, stage one isn't just learning what buildings are in one tile. It's learning that if tile A shows a highway ramp and tile C shows a high-density apartment block, then tile B, the one that's missing, probably shows an access road connecting them. It's learning the logic of the map itself.
Precisely. And the end result of stage one is Titan NV, a model that deeply understands histology's morphology and its spatial context.
So quick recap then. Stage one gives us this general vision encoding using a vision transformer in the feature space trained on, nearly 340,000 slides?
That's right.
But this brings us to the biggest technical headache: scale. If that feature grid is so enormous, how on earth do they handle the long context modeling?
That is the architectural innovation that really sets Titan apart. Standard models, they just fall apart because an entire WSI can generate over 10,000 tokens in that feature grid. And with attention mechanisms, the computational cost explodes quadratically.
Yeah.
It's infeasible.
So what's the solution?
Titan's solution is a really clever strategy called train short, test long. They train the model on those smaller, manageable 8K by 8K regions.
Okay.
But they need a mathematical way to make sure that knowledge reliably extends to the full, potentially gargantuan WSI during actual use. And they do this using something called 2D attention with linear bias, or ALiBi.
ALiBi, I know that from large language models. It basically adds a penalty for distance, right? So how do they translate that from a 1D text sequence to a 2D image grid?
They extended it beautifully.
Yeah.
In Titan, ALiBi modifies the attention score, so how much focus the model places on any two patches, by adding a negative linear bias. The farther apart two features are in that 2D grid, the larger the negative bias becomes.
So the model is, by design, spatially conservative. If two bits of tissue are microscopically miles away from each other on the slide, ALiBi just ensures the model doesn't waste energy trying to find some deep contextual link between them.
Correct. It respects the biological reality of distance. And this is absolutely critical for that test long phase. It lets Titan extrapolate its understanding across an entire gigapixel slide without memory failure. It tames the scale challenge.
Okay, so scale is tamed. Now what about the language?
Now we shift to the multimodal aspect. Stages 2 and 3. This is the vision language continual pre-training. Because vision-only models like Titan V, powerful as they are, they're missing all that rich clinical reasoning locked away in pathology reports.
Right, this is where the language alignment comes in. But wait, before we get to the actual clinical reports, you said stage 2 uses hundreds of thousands of synthetic captions
That's right.
generated by that AI copilot, PathChat. Why? Why use fake captions for this fine-grained alignment instead of just using the real reports? Isn't that a bit risky?
That's a crucial question, and it really gets to the limitations of real clinical data. Pathologists, they write reports for diagnosis, for treatment, so a typical report gives a high-level summary: invasive ductal carcinoma, grade 2.
Pretty concise.
Very. It rarely includes those microscopic fine-grained details like cells exhibit marked nuclear pleomorphism with irregular chromatin clumping.
Ah, I see. So the actual reports provide the answer, the final diagnosis, but the synthetic captions provide the reasoning. They teach the low-level visual concepts needed to get to that answer.
Exactly. Stage 2 is all about fine-grained alignment. It aligns those 8K by 8K regions of interest with 423,000 of those really detailed synthetic captions. This phase teaches Titan the specific vocabulary of morphology at a local level.
So it learns to recognize those complex cellular patterns that are super important but might not make it into a short report.
You've got it. Then, once Titan masters those fine-grained visual concepts in stage 2, it moves to stage 3, global alignment.
And this is where the real reports come in.
This is where it aligns the entire WSI with those 182,000 actual clinical pathology reports. This is the pivot point. Is where the model connects local microscopic observations with global diagnostic terms and clinical reasoning. It learns to speak the language of the hospital.
That is a true three-stage master plan. First, general vision encoding. Second, fine-grained language learning with AI-generated descriptions. Third, high-level clinical reasoning with actual doctor reports.
It ensures the model is both microscopically precise and clinically accurate. It's highly effective.
And that structured pre-training, that brings us to the big question, the ultimate proof point. Performance. Does all this complex engineering actually lead to better clinical outcomes, especially in those really tough, rare disease cases?
Well, let's look at the numbers.
Yeah, where does Titan stand when you benchmark it against other big foundation models like Prism or GigaPath?
Titan's generalizability is, frankly, stunning. It was tested across 62 diverse tasks, everything from classifying tissue types and grading tumors to predicting molecular biomarkers and even patient survival.
And the result?
The aggregate result is staggering. Across a whole suite of subtyping tasks, Titan showed an average performance increase of plus 8.4% over the next best model. In clinical AI, that is a massive jump.
It really is.
But the most important area is that low data regime, the few-shot learning. Remember those rare cancers where you might only have one or two examples?
Mm-hmm.
Titan showed superior data efficiency. It's a direct result of its robust pre-training. On this really challenging task, OT108, which is all about rare pan-cancer subtyping, Titan blew the other encoders out of the water.
So what does that mean in practice?
Functionally, it means if a pathologist discovers a new, extremely rare cancer variant, they might only need to feed Titan a single example to begin classifying it reliably. That could drastically accelerate diagnosis.
That immediately saves lives and research time. Okay, now what about the unique things you can do with the language component, this cross-modal functionality? Can Titan actually diagnose using only text?
Yes, this is zero-shot classification. So a pathologist can input an entire slide and then just type a diagnostic question, a text prompt like, identify the subtype from this list, without the model ever being specifically fine-tuned for that task.
It's just using its pre-learned connection between vision and language.
Exactly. And the results here were game-changing. On the 30-class eBrains subtyping task, Titan doubled the balanced accuracy of the previous leading model, Prism. It showed a plus 121.9% balanced accuracy gap.
Doubling the performance of a leading model in zero shot. That is the definitive confirmation that the vision language alignment worked.
It demonstrates true, deep generalization. The model isn't just memorizing, it's reasoning.
So it's got a truly portable understanding of pathology.
And this extends to language output as well. For report generation, Titan substantially outperforms Prism by an average of 161% across measures of textual quality. The reports it generates correctly capture the tissue site, the diagnosis, the tumor grade, all the relevant details. It's an immediate assistant for an overworked pathologist.
Okay, finally, let's talk about the clinical utility of rare cancer retrieval. This sounds incredibly important.
It is. When a pathologist faces a complex or rare case, the gold standard is to retrieve similar historical cases, both the slides and the reports, from the hospital's archive for comparison.
So it's like having instant access to decades of institutional knowledge, indexed not just by text, but by what the tissue actually looks like under a microscope.
Precisely. And Titan significantly outperforms other encoders here, with a plus 14.8% higher average accuracy in retrieving relevant cases. But crucially, think about its robustness to what we call domain shift.
You mean, does it work in any hospital, regardless of their specific equipment?
Yes. On the rare cancer external cohort, which came from a Japanese institution, completely new scanners, new staining methods Titan achieved, plus 30.8% higher accuracy than the next best model. That proves it's a true general-purpose tool.
And the case study you shared proves the clinical relevance, not just the technical accuracy. Retrieving a query slide for something called a paraganglioma,
Yes.
it successfully returned other paraganglioma slides, but also highly similar pheochromocytoma slides.
And that is the ultimate proof of deep learning. Those are two closely related, rare neuroendocrine tumors. Titan didn't just match labels. It recognized the underlying shared morphology, the shared cellular structure. It connected two clinically related diseases. That's so much more useful to a pathologist than just finding an identical image.
So if we just step back and look at the big picture, Titan's three-stage approach, starting with this massive vision encoding, then using AI-generated text for that fine-grained teaching, and finishing with clinical report alignment. This has successfully created the most robust and versatile pathology embeddings we've seen to date.
And the best part is the scalability. The framework is just inherently designed to ingest more WSIs, more clinical reports, and crucially, more of those detailed synthetic captions from tools like PathChat. The model's performance is only going to climb.
Which means it can offer immediate clinical benefit in those low data scenarios, starting right now.
Right now.
And that brings us right back to the question of synthetic data, which so dramatically improved Titan's ability to learn morphology. We are now using AI-generated data to train foundation models that will directly inform a clinical diagnosis.
It's a powerful new feedback loop.
It is. So considering the stunning success of this synthetic enhancement, this use of AI-generated captions to teach an AI model, what new ethical and clinical boundaries do you think computational pathology will cross when the majority of its training data is synthetically enhanced or generated? If the teacher is also an AI, how do we define the ground truth moving forward? Something for you to consider as you digest this deep dive.